Hello and welcome to this first video of a playlist about the preparation of fluoroalkylarenes. In this video, we'll have a look at the properties of fluorinated organic compounds, including their acidity and general reactivity. Then I'll show you examples of the preparation of trifluoro and difluoromethylarenes from unsubstituted arenes, arylboronic acids, and aryl silanes. Some important biocides contain difluoromethylpyridines or pyrazoles, and better syntheses of these compounds are therefore of interest. Because such reactions often involve fluoroalkyl radicals, the regio and chemoselectivities can be unexpected and difficult to predict correctly. The second video of this playlist is about fluoroalkylations of aryl halides, esters, and of organomagnesium or zinc compounds prepared from aryl bromides. In part 3, we'll have a look at ring-forming reactions that yield fluoroalkylarenes, mostly heteroarenes, for instance cyclocondensations of trifluoromethyl ketones or cycloadditions. The last video of this playlist is about preparing fluoroalkyl groups from other functional groups. As usual, there is a copy of the slides and transcript under the Posts tab of my channel. Compared to the CH bond, the carbon-fluorine bond is less polarizable, and the attractive forces between fluorinated molecules are weaker than those between simple alkanes. The latter are held together by spontaneous polarization and dipole-induced dipole interactions, the so-called London dispersion forces. These are absent in fluorinated compounds. Thus, methyl iodide boils at 43 degrees Celsius, while the heavier trifluoromethyl iodide already boils at -23 degrees Celsius. Perfluoroalkanes are not miscible with alkanes, because it costs energy to separate alkane molecules from each other, but no energy is gained by the interaction of a perfluoroalkane with an alkane. Perfluoroalkanes are thus hydrophobic, but also lipophobic and thermally stable, and Teflon is therefore used to coat frying pans. Moreover, fluorinated alkanes do neither burn nor form explosive mixtures with air. If we compare toluene to trifluoromethylbenzene, we see that despite the higher molecular weight and stronger dipole moment, trifluoromethylbenzene has a lower boiling point than toluene. In the development of new drugs and agrochemicals, trifluoromethyl groups offer an interesting possibility to fine-tune the properties of biologically active compounds. Here are some drugs and biocides that contain trifluoromethyl groups. Insecticides and fungicides tend to be extremely hydrophobic, and broflanilide even contains a perfluoropropyl group. Perfluoroalkanes and trifluoromethyl groups are chemically stable and unreactive. When methane is fluorinated, the stability of the product increases with each additional fluorine atom. Thus, if we hypothetically convert methyl fluoride into trifluoro or tetrafluoromethane and methane by redistributing the fluorine atoms, such reactions are highly exothermic. Converting methyl chloride into tetrachloromethane, however, is endothermic. The main reason for this stabilization is electrostatic attraction between the partial negative charge at fluorine and the positive charge at carbon. As shown in this table, upon increasing fluorination, the carbon-fluorine bonds become shorter, and the partial positive charge at carbon increases. With each additional fluorine atom, the carbon-fluorine bonds become less covalent and more ionic, with a decreasing contribution of pi bonding. If stabilization was caused by hyperconjugation, we would expect an increasing pi bond order between carbon and fluorine, and a decreasing partial negative charge at fluorine upon additional fluorine substitution. The partial negative charge at fluorine almost remains unchanged, however. Thus, hyperconjugation does not contribute significantly to the stabilization of tri- or tetrafluoromethane. The equilibrium acidity of trihalomethanes is difficult to measure because the anions are unstable and fragment into halides and dihalocarbines. However, base-induced hydrogen-deuterium exchange is faster than carbene formation and can be used to estimate the pKa of trihalomethanes. For trifluoromethane, this exchange is slow compared to that of the other trihalomethanes. And, although fluorine has the highest electronegativity, trifluoromethane is the weakest acid. This is not a contradiction. The gas phase acidity of protic acids depends on the homolytic bond strength to hydrogen, but also on the electronegativity of the hydrogen-bound atom, and does sometimes increase when the bond to hydrogen becomes stronger.
Here you can see the bond dissociation energies, electronegativities, and the pKa of some acids, ordered as in the periodic table of the elements. When going from methane to hydrogen fluoride, the bond strength increases, but the electronegativity also increases, and hydrogen fluoride is the strongest acid, despite its strong hydrogen-fluorine bond. When descending from hydrogen fluoride to hydrogen iodide, however, the electronegativity drops, but because of the weakening bond strength, hydrogen iodide is a stronger acid than hydrogen fluoride.
Trihalomethanes behave like hydrogen halides. The standard enthalpy of formation of trifluoromethane is very low compared to the other trihalomethanes. Thus, although fluorine is best at stabilizing carbanions, and the trifluoromethyl anion has therefore the lowest energy of the four trihalomethyl anions, the energy gap between trihalomethane and its anion, as indicated by the red arrows, is largest for fluorine and smallest for iodine. This could be caused by steric repulsion between the halogens, which is largest for iodine and is relaxed upon deprotonation. Moreover, in the anions, the filled halogen sp3 orbitals and the lone paired carbon repel each other. This repulsion is strongest for fluorine because its sp3 orbitals have a similar size as the carbon orbitals and overlapped best with these, and because the carbon-fluorine bond is short. One frequent explanation for the low acidity of trifluoromethane compared to chloroform is that in the trichloromethyl anion, electron density is distributed into the empty d orbitals at chlorine. This is, however, unlikely because the d orbitals have a much too high energy level to be accessible. There is little to be gained by adding one more electron to chloride and reducing it to a dianion. Argon would actually be easier to reduce to an anion than chloride to a dianion. If you want to learn more about the impact of fluorine on the acidity of organic acids, here are some articles on this topic.
Other reactions that require the formation of trihalomethyl anions will also be slower with fluorine than with the other halogens. For example, if we compare the rate of thermal decarboxylation of trihaloacetic acids, trifluoroacetic acid is by far the most stable, and trichloro and tribromoacetic acid decarboxylate much faster. Similarly, trifluoromethyl ketones are stable and do not undergo haloform cleavage as readily as trichloromethyl or tribromomethyl ketones. Trifluoromethyl ketones are strong electrophiles and react with water and alcohols, yielding stable hydrates or hemiacetyls. Trifluoromethyl arenes are usually more stable than trichloromethyl or tribromomethyl arenes. The latter react quickly with water, even at room temperature, first to benzoyl halides and then to benzoic acid. Trifluoromethylbenzene is difficult to hydrolyze, however, and resists heating with sulfuric acid. There are exceptions, however. Trifluoromethyl arenes with a hydroxy or amino group in positions 2 or 4 sometimes eliminate fluoride under relatively mild conditions, as in this example. Trifluoromethyl groups sometimes behave like halides and may be eliminated or substituted by nucleophiles. In this example, a Bisch trifluoromethyl imidazoles was aromatized by heating with potassium fluoride in DMSO. Leaving groups in positions 2 and 4 of pyridines are easy to displace, and, as shown here, trifluoromethyl groups at these positions can also be substituted, for instance by hydride. Some words about the mechanism of trifluoromethylations. Direct nucleophilic substitutions at trifluoromethyl electrophiles do not work well. Most fluoroalkylations proceed by intermediate fluoroalkyl radicals, which are easy to generate.
These reactions can often be catalyzed by copper, which further stabilizes radicals as ionic or neutral organocuprates, but transition metal catalysis is no strict requirement. When trifluoromethyl radicals add to arenes, an oxidant is required to aromatize the product and to maintain the radical chain. In this sketch, this oxidant is tert-butyl hydroperoxide, and the trifluoromethyl radical precursor either a silane or a cuprate.
Trifluoromethyl electrophiles do not react with nucleophiles as expected. Here, trifluoromethyl triflate was treated with various nucleophiles, for instance pyridine, triethylamine, iodide, and phenolithium. In none of the experiments, a trifluorometallation of the nucleophile occurred. Sulfur was the preferred site of nucleophilic attack, not carbon. A more effective electrophilic trifluoromethylating reagent is the iodonium carboxylate shown here. This electrophile trifluoromethylated sodium benzene sulfonate, albeit in low yield only. With the aid of a copper complex, the yield could be increased, however.
Unlike trifluoromethyl anions or cations, trifluoromethyl radicals are easy to generate. Although the thermal decarboxylation of trifluoroacetic acid is slow, heating its sodium salt with iodine and DMF gave trifluoroiodomethane in only 1 hour by a radical chain reaction. Under similar conditions, non-fluorinated sodium acetate only yielded traces of methyl iodide, because the methyl radical is formed more slowly than the trifluoromethyl radical. I've sketched here the most common precursors of trifluoromethyl radicals. These include aryl iodonium salts, sulfonium salts, cuprates, trifluoromethyl iodides, sulfonates, silanes, and sulfonyl fluorides.
I'll show you now some specific examples of the use of these reagents to fluoroalkylate arenes in the order given here. As expected, these reactions work best with electron-rich arenes because fluoroalkyl radicals are electron-deficient and react fastest with electron-rich olefins and arenes. One advantage of carbon-centered radicals is that they only abstract hydrogen from silanes or stananes, but rarely from alkanes, alcohols, or amines. Unprotected anilines can therefore be fluoroalkylated directly. Here, aniline was trifluoromethylated with an iodonium carboxylate and 10% of nickel hydroxide. The yield was high, but the regioselectivity was only low.
With the sterically more demanding perfluorinated isopropyl iodide, a high yield of only one isomer resulted in this instance. The fluoroalkyl radical was generated by single electron reduction with dithionite, and the reaction mixture was kept alkaline with sodium carbonate to prevent protonation of the aniline by hydrogen iodide. Protonated anilines are less electron-rich and less reactive than non-protonated anilines. Acylated anilines have been trifluoromethylated with trifluoromethane sulfonate as radical precursor and terp-butyl hydroperoxide as oxidant. In this example, the fluorinated radical was generated from an alkyl bromide and catalytic iron. The aromatic bromide did not react under these conditions. Despite the large excess of radical precursor, the yield of monoalkylated product was high. Also in the previous examples, only one fluoroalkylation occurred, probably because fluoroalkylated arenes are no longer electron-rich enough to undergo a second alkylation.
Here, a similar reaction was catalyzed by a nickel complex, and a good yield was attained with only 2 equivalents of radical precursor. Also, aryl ethers can be fluoroalkylated directly with fluoroalkyl radicals. Here, the latter were generated from a silane and diacetoxyiodobenzene as oxidant. The regioselectivity was poor in this instance. In this example, mainly one isomer was formed, and despite the large excess of radical precursor, the fluoroalkylation occurred only once. Benzene is less reactive than anilines, ethers, or alkyl benzenes. Here, benzene was trifluoromethylated in fair yield with a trifluoromethyl iodonium carboxylate and arenium catalyst. Also, trifluoroacetic acid can serve as a source of trifluoromethyl radicals. Here, catalytic silver carbonate and an excess of potassium persulfate were the oxidants. Because no excess of benzene had been used, 10% of dialkylated benzenes resulted as byproducts. With a large excess of benzene, however, it is possible to attain high yields of benzotrifluoride. Here, a silane was the source of trifluoromethyl radicals, and silver triflate was the oxidant. I'll show you now some examples of fluoroalkylations of transition metal chelates. One possible mechanism is sketched here, in which both a fluoroalkyl radical precursor and an oxidant to regenerate palladium-2 were required. In this example, the radical precursor was a sulfonium salt and the oxidant was copper acetate. Here an indolene was trifluoromethylated, again with a trifluoromethyl sulfonium triflate, catalytic palladium acetate, and copper acetate under acidic conditions. Interestingly, no dehydrogenation of the indolene occurred. Even benzolamines can be fluoroalkylated this way without oxidation to benzaldehydes or benzoic acids. Ruthenium complexes can be used to fluoroalkylate certain arenes at the meta position of a chelating group, as shown here. With only 5% of ruthenium, a high yield of product was obtained.
It seems that ruthenium chelates react with electrophilic radicals para to the metal. In this instance, the radical precursor also acted as oxidant for the reoxidation of ruthenium-1 to ruthenium-2. Indoles react with fluoroalkyl radicals preferentially at position 2. Position 3 is more electron-rich, but sterically less accessible than position 2, what may be the reason for this unexpected regioselectivity. Here, catalytic palladium acetate and one equivalent of silver carbonate were used, but transition metal catalysis is not strictly required for this reaction. In this example, scatol was trifluoromethylated with a sulfonium salt and 5% of a nickel catalyst. In DMSO, the reaction already proceeded at room temperature. Protected tryptophan can be fluoroalkylated with a sodium sulfonate. Persulfate is oxidant, and 10% of copper-1 acetate as catalyst. This reaction can also be achieved with a sulfonium salt, but without any transition metals, as in this example. Like indoles, also benzofurans are preferentially fluoroalkylated at position 2. In this example, first a difluoroacetic ester was prepared by copper-catalyzed fluoroalkylation and then saponified and decarboxylated to a difluoromethylbenzofuran. As discussed above, fluorinated carboxylic acids do not decarboxylate readily, and in this instance, heating to 200 degrees Celsius for 16 hours was required.
Direct difluoromethylations can sometimes be achieved by heating arenes with difluoroacetic anhydride and a palladium catalyst. In this example, the yield of difluoromethyl-benzoxazole was low, however, and yields were lower still with benzothiazoles or imidazoles.
Donor-substituted pyridines usually react with fluoroalkyl radicals ortho or para to the electron-donating group. In this example, 2-hydroxypyridine mainly gave 3-trifluoromethyl-2-hydroxypyridine upon reaction with trifluoroiodomethane and hydrogen peroxide in the presence of 30% of ferrocene. 2-hydroxypyridines are mixtures of pyridine and pyridone tautomers, the ratio being dependent on the solvent and the substituents. This example is similar to the previous one, and fluoroalkylation occurred again at position 3. Interestingly, even acceptor-substituted pyridines can still be fluoroalkylated, despite their low electron density. Here, difluoromethyl radicals were generated by oxidation of a zinc sulfonate with tert-butyl hydroperoxide. Although one equivalent of trifluoroacetic acid had been added to acidify the reaction mixture, either no trifluoromethyl radicals were formed or these were too electron deficient to add to the pyridine. Also, difluoromethyl silanes can yield difluoromethyl radicals upon oxidation. Here, phenanthroquinone was the oxidant, and both an excess of potassium tert-butoxide and copper cyanide was also required. No aromatic nucleophilic substitution of bromide occurred.
In this example, oxidation of trifluoroacetic acid with silver carbonate yielded trifluoromethyl radicals, which added with high regioselectivity to an N-methylpyridinium salt. Nucleophilic attack of iodide or carbonate at the methyl group then brought about dealkylation. Quinolines are much more reactive than pyridines. Here, a dihydroquinoline was prepared in situ
by reduction with a silane. Treatment with a trifluoromethyl iodonium salt and DDQ
then gave a 3-trifluoromethylquinoline. With monocyclic pyridines, the yields were lower though. Arylboronic acids, aryl silanes, and more nucleophilic metylated arenes undergo aromatic electrophilic substitutions with similar reagents as unsubstituted electron-rich arenes. One can therefore fluoroalkylate metylated arenes with the same reagents as those required for unsubstituted arenes. Here, phenylboronic acid was converted into benzotrifluoride with an excess of a trifluoromethylsilane and silver carbonate as oxidant. A small amount of biphenyl was formed as a byproduct. Sulfonium salts combined with copper powder can also convert boronic acids into trifluoromethyl arenes, as shown here. The trifluoromethyl sulfonium triflate was prepared from a diaryl thioether and triflic anhydride. Thus, similar trifluoromethylations may also be achievable with triflic anhydride as radical source and only catalytic amounts of thioethers. In this example, a boronic acid was selectively difluoromethylated with difluoroiodomethane and a palladium catalyst. A trimethylsilyl group remained unchanged under these conditions. A similar reaction as on the previous slide can also be brought about with certain activated difluoroacetyl anilides.
In this example, a trifluoromethylsulfonium ylide was used to trifluoromethylate boronic esters. The reaction was catalyzed by a copper phenanthrene complex and already proceeded at 10 degrees centigrade.
Here, a boronic ester was difluoromethylated with stoichiometric quantities of a palladium carbene complex. This is of course way too expensive for any practical application, but such reactions can shed light on their mechanism and facilitate the development of catalytic fluoroalkylations. In this example, an activated boronic ester was difluoromethylated with a sulfonium ylide. Again, a trimethylsilyl group in the starting material remained unchanged. Trifluoroborates show a similar reactivity as boronic esters and can also be fluoroalkylated, for instance with sodium trifluoromethane sulfonate, copper chloride, and tert-butyl hydroperoxide. Although in two of the previous examples, trimethylsilyl groups did not react under mild fluoroalkylating conditions, they can do so at a higher reaction temperature or otherwise more vigorous conditions. Here, a combination of trifluoromethyl copper, silver fluoride, and benzoquinone in DMF gave 70% of the expected trifluoromethylarene. So what about potential side reactions? Because of the many reagents often required for fluoroalkylations, a lot can go wrong. Oxidants can dimerize electron-rich arenes or yield quinones or quinone methides. Arylboronic acids and silanes can be hydrolyzed to unsubstituted arenes by protic solvents or transformed into less reactive intermediates. Here, for instance, a boronic ester reacted with fluoride to a trifluoroborate, which underwent difluoromethylation only slowly. Sometimes fluoroalkylation might also occur at some heteroatom, as in these two examples. Depending on the base chosen, a 2-hydroxypyridine was either alkylated at oxygen or at nitrogen by the same difluoromethylating reagent. Thus, fluoroalkylations may require some optimization and careful analysis of the products. Many more examples have been reported recently, and here is a selection of recent articles, which you can also find in the description of this video. In the next video of this playlist, we'll have a look at the fluoroalkylation of aryl halides or sulfonates by displacement of the leaving group. See you there.